Supercomputers needed weeks. This AI solved it in seconds. Imagine giving a supercomputer a physics problem so difficult that even the fastest machines on Earth would need weeks or longer to approximate the answer. Now imagine an AI solving that same problem in seconds. This isn't science fiction. A new artificial intelligence framework called THOR has just done exactly that. And the problem it tackles isn't trivial. It's one of the most notoriously difficult calculations in physics, a mathematical puzzle that has frustrated scientists for more than a century. If the claims hold up, this breakthrough could dramatically speed up discoveries in material science, chemistry, and even future energy technologies. But what exactly did this AI solve, and why does it matter so much? To understand the significance of THOR, we have to talk about a fundamental challenge in physics known as the configurational integral. This calculation lies at the heart of statistical mechanics, the field that explains how the behavior of individual atoms and molecules gives rise to large-scale properties like temperature, pressure, elasticity, and phase transitions. In simple terms, if you want to know how a material behaves, whether a metal melts, how crystals form, or how materials respond to extreme pressure, you need to understand how every atom interacts with every other atom. That's where the nightmare begins. Each atom can move in multiple directions and interact with many neighbors. As you add more atoms, the number of possible configurations grows exponentially. Physicists call this the curse of dimensionality. With just a few atoms, the math is manageable, but real materials contain trillions upon trillions of atoms. To deal with this, scientists have traditionally relied on indirect computational tricks, like molecular dynamics simulations or Monte Carlo methods. These simulate countless atomic movements and gradually approximate the answer. But even with powerful supercomputers, these simulations can take days, weeks, or even months, and they still provide only approximations. This is where the new THOR AI framework enters the picture. Developed by researchers at the University of New Mexico and Los Alamos National Laboratory, THOR approaches the problem in a completely different way. Instead of simulating every atomic interaction step by step, it uses a combination of tensor network mathematics and machine learning potentials to attack the problem directly. Here's the clever idea. The massive calculation that describes atomic interactions can be represented as an incredibly high-dimensional dataset. Normally, that dataset is so large that it's practically impossible to compute. THOR compresses this information into smaller interconnected structures using a mathematical technique known as tensor network cross-interpolation. Think of it like compressing a huge movie file into a tiny zip archive, but without losing the important information. By breaking the calculation into smaller, linked pieces, the AI can reconstruct the final answer extremely efficiently. And the results are dramatic. Calculations that previously required thousands of hours of supercomputer time can now be performed hundreds of times faster, sometimes finishing in seconds while maintaining high accuracy. The system also detects symmetry patterns in crystal structures, which allows it to skip redundant calculations. In physics terms, that's a massive optimization. Researchers tested the framework on several challenging materials problems, including metals like copper, high-pressure noble gases such as crystalline argon, and complex phase transitions in tin. In each case, THOR reproduced the results of traditional simulations while running more than 400 times faster. At first glance, this might sound like a niche academic achievement, but the implications could be enormous. Material science is the foundation of modern technology. Every battery, semiconductor, spacecraft alloy, or fusion reactor component depends on understanding how atoms behave under different conditions. Right now, discovering new materials is painfully slow. Researchers often rely on trial and error combined with expensive simulations. But if tools like THOR can evaluate material properties almost instantly, the entire research process could accelerate dramatically. Imagine being able to rapidly test thousands of new alloys for stronger aerospace materials, or simulate atomic structures for next-generation quantum computers, or design better catalysts for clean energy production. In other words, faster physics calculations mean faster technological progress. However, there's an important nuance that many headlines overlook. THOR didn't magically eliminate complexity from physics. It reorganized the problem mathematically so that it becomes computationally manageable. That distinction matters. The breakthrough comes not just from AI, but from combining advanced mathematics, tensor networks, and machine learning potentials. In other words, the real innovation is the fusion of disciplines. AI augmenting traditional theoretical methods, allowing researchers to explore areas of physics that were previously computationally unreachable. If THOR proves reliable across more material systems, we may be looking at a major shift in computational science. For decades, researchers assumed that directly solving the configurational integral for realistic materials was practically impossible. The dimensionality of the problem made it seem hopeless. But tensor-based approaches like THOR suggest that the landscape is changing. In the future, similar AI-driven frameworks could be applied to other extremely complex scientific problems, including protein folding and drug discovery, nuclear fusion plasma modeling, climate simulations, and quantum materials design. Even more interesting is the possibility of combining these systems with automated scientific discovery platforms. Imagine an AI pipeline where one system proposes new materials, another simulates them instantly, and a third predicts real-world performance. That kind of workflow could compress decades of research into months or even weeks. For more than 100 years, physicists have wrestled with calculations so large that solving them directly seemed impossible. Now, with tools like THOR, we're beginning to see a new era where AI doesn't just speed up science, it reshapes what's computationally possible. And that raises an intriguing question. If AI can already solve problems once thought unsolvable in seconds, what other scientific mysteries are waiting for the right algorithm to unlock them? Because the next major discovery might not come from a bigger supercomputer, but from a smarter way of thinking about the math itself.